The classes operators as small position. After school, I decided to study physics, but eventually, I came to software engineering. And the moment I work for Kayak for almost 7 years now, and Python is very one of my favorite tools to work with. So, and this is my first time speaking in a fighter of operates. Thank you. How do you hear anybody say, like, two posts, all good? Yeah, okay, cute, wow. Oh yeah, curious now. Please, neighbors, raise your hands. You have never been in a class of Python. Cool, that's quite a bunch. I hope to share something useful either way. Alright, let's get into it. So what is our agenda for today? First of all, we will answer the question of why do we EDV classes. Then, we will look into the instruments that we will use to create friendly Python classes. Further, we will define it. Then, we will step through examples of code for GGig friendly metric. Moreover, we will practice. We will start by expanding the functionality of a metric, and ultimately we will build an analytical queue. So why you need classes in the first place? And by we don't actually use them, but they help to organize code to when the complexity of the app grows, and most good apps utilize classes. However, if we have a simple script, there is no need to have classes in Python. And sometimes we might have to use classes because the library that we wish to make use of is built in classes. Yet when we use this library, we don't necessarily need to inherit classes. For example, when we splice and dice data with the pandas library, we don't inherit its classes, even though the library is built with classes. On the contrary, when we use the web framework Django, we almost always inherit classes. So you might ask, do I need to know how to create friendly Python classes if I have to use them? I would say that not really, but you might benefit from the knowledge. And if you are creating Python applications that benefit from them, then it is a very easy thing to know. Moving on, what instruments will be used to create a friendly class? We will use data classes, operator overloading, and composition over inheritance principle. If you don't know what they are, that's okay. We will get to know them. Alright, let's define friendly Python classes. Let's look at them as our friends in real life. Just like our friends, they are easy to understand and to talk to. Such classes are easy to read and write. We understand each other without words. We can use mathematical operators between their objects. They are easy to reach. Such classes are easy to call. I have added an asterisk on the second property because we don't always need to understand each other without words. Therefore, we don't always need to support mathematical operators. However, if we get benefit from them, that's a very weak benefit. Having said that, we don't need to get every property of a friendly class for it to be considered friendly. Having one property makes a class already friendly. Let's first forge a class that is key to read and write. Alright, let's turn to code. Here we have the traditional way of describing a class to which we can pass arguments while initializing. We can pass an alias and a field state. Let's think of it as an analytical metric that we could later use to query an SQL-like database with. Let's create a revenue metric by summing the values of the revenue code. Okay, Do you know what the response will be if we now enter into the Python interpreter? Please raise your hand if you think it will be A. D? Does anyone think it will be C? And if you limit D, please raise your hand. Okay, I see. So most of you know the answer. That's correct. If we get the name of the module, name of the class, and the address in the memory. It could be useful for a computer scientist, but on the other hand, the information is redundant, abusive, and there is not much information about the object itself. Version 2. Let's have a look at the failure representation. For this, we have to define the redundant method of the class. So we define the method. We return the class at the arguments that were asked by creating the object. By the way, thunder stands for level underscore. And we create the memory metric again. What do you think will the response be now? Yeah, it's just like you described. It is a much randier response right now, and if we were to debug this object, only from its representation, we could already know what class does use and what arguments were asked it. I also wonder if you have found this topic interesting. The object creation as well as the representation expressions are the same. Thus, we can easily recreate such object using Git's representation. Ideally, that's how the interpreter method works. This leads me to my next point. Let's utilize data classes. We can simply import and use it as a decorator above a class. It already has all the logic that we described earlier. It has even more logic, but that is not relevant to us for this presentation. Note that we have to type in the data types of the variables in order for the data class to turn them into class arguments. We hit enter to see what is the interpreter going to answer us. And we get the same response as before. We can see that the data class reduces us a lot of boilerplate code as well as supports us while debugging. Now you would naturally ask me, Ąžuolas, but do we always have to pass the arguments now? And we not have the whole values or static class variables? To this I can answer that yes, we can. We don't have to pass variables as we go in advance. We can also set a default value for that. But do you believe my words? Let's check if by 52% that I'm not liked. Let's set the default value in the data class. We simply need to define it. And we can still override to creating that object. Here we do have defined the default value of the translation variable as metrica. It's a metric in Lithuanian. We could create a revenue metric again. And this is what we get. In the representation, we can set the default value of the variable that we specified inside the class but do not pass as an argument. Now we will set the static class variable in the data class. We define the static class variable product as data analysis. Can you notice what is different from the default value? I think I heard that we have not typed into the data type. That's correct. Let's initialize a revenue metric again. Here we have the exact same response as before. However, if we access the product variable of such an object, we still get the value we described, that is data analysis. What about the even-done-there methods? What if we wish to have some special logic during object initialization? We don't look at the data classes. We can prescribe the logic inside the posted done there method, so now it's just inside the other method. Here, for example, we store the data of the log generation inside the post-knitting method under the break variable. We create a reference method once again. When we access the data break variable, we get the dime was created. Moving on, we will use mathematical operators to create objects out of the existing one. Now we will implement the division of metrics since it can be of great use in analytics. In my opinion, this elevates metrics classes to new heights. We never know what metric a user would like to look at if they can derive any metric that they wish out of existing columns. This saves a lot of repetition as well. In order to do that, we define the TrueDiv blunder method. When a metric is divided, Python interpreter calls the TrueDiv methods under the vote. This method creates and returns a new metric object, but we derive the new alias by inserting a deletion operator between the aliases, and we do the same on the field. Let's look into some examples now. We create a rarity metric as well as a sessions metric, and we wish to have a revenue per sessions metric. Thus, we do the definition. What will be the response? You know, exactly this. We will get the derivative revenue per sessions metric with aliases as well as fields separated by a Lilish copper meter. Note that we don't really need to use operators. We simply apply that TrueDiv method, but it is nice to have operator support. Therefore, we explore it. Here we derive another useful metric. First, we define the searches metric. Then, we simply divide the revenue metric out of the searches metric. Hence, we get a very graceful revenue per searches metric. Now, I'd like to ask you if it was easy to grade metrics so far. Please raise your hand. All right, I've seen some hands that's put here, put C. I don't know of an easier way to grade the metrics. All right. All this time we have actually used composition to grade metric objects. Thus, we have applied the position over hierarchies principle. It simply says to favor object or position over class prefix. What about the prefix? Let's have a look at it to compare. Let's apply the base metric that do inherit to define other metrics. Here we don't need data classes because we will inherit this class. For a nice debugging experience, we can have the record method as well. Then this is how we can define various metrics by inheriting the base metric, a revenue metric, a sessions metric, and a searches metric. We can see that now we have 4 classes total instead of 1, and then the inheritance tree grows. However, this is not the problem here. The proposition over inheritance principle was created to tackle a problem called class explosion, for which we cannot see here because the code is simple. We will not try to recreate class explosion here since this is not the aim of this presentation. However, we can see that instead of calling the class with variables, we always have to inherit and describe a new class. Thus, it requires us to overcome more obstacles to create a new class. Let's now look at the metric objects with this approach. To give us skill same representation. However, if we try to recreate it through the representation, we would get an error. As most of you know, Okay, now maybe it was meant for you to follow for one or another reason. This is the key takeaway. Here is a training class. Such a class structure will grant you quick and simple creation of a class as well as an object. Besides, it will support you well with debugging. Additionally, we can support mathematical operations and create new objects on the fly. Having division supports, revenue metric division by a sessions metric produces as a revenue per sessions metric. Do you have any questions so far? Okay, let's practice. Now we will add division by numbers. First, we check if the instance is an integer or float. Then we do everything the same as with classes. The only difference here is that the argument caller is not the class here, but an integer or float. Accordingly, we will need to access its alias and field. Let's have a look and an example. We divide our regular metric by 1000 so that we get the sub-10 thousands. Here we can see the formatted alias and the correct scale expression of new derived metric. But it be divided by string then? Well, we have not defined a logic, so we will get an error. But it is possible to provide a logic for such a case as well, if we wish so. Okay, now we will define number division by metric. For that, we will use the TrueDiv method. RTrueDiv. RTrueDiv is called on the right-hand side member of the division. In the left-hand side member, returns not implemented. We have defined it exactly as TrueDiv, but switched the order of the members of the division. Thus, how do you divide RTrueDiv? Now our metrics can divide numbers. Here we can see how it works. Dividing 3.40 by radial metric, we get non-implemented. And then by your interpreter runs the RTrueDiv method of the right-hand side member of the division, the revenue metric, and we get the correct result. Let's take a look at an example. Say, we had a revenue target of $10,000, and dividing it by revenue, we can get the part of the target revenue that we hit. Again, we have clear ABS as well as a correct scale expression for such a metric. Now we will look to map multiplication as well. For this, we distract the model.the method. We do everything the same, except that we use a start between aliases and fields. Our goal is easier to design because the order of the factors does not matter. Let's now bring an RPM metric. Do you remember what RPM stands for? Maybe somebody said it, I got it here, but it is Arabic Kamila, which stands for 1,000 this searches in this space. Thus, it is revenue per 1,000 searches. So this is how we can derive the metric by dividing our already refined revenue metric by searches metric and multiplying it by a constant. Moreover, we can define metrics which are a little more complicated scale expressions. Let's divide about sessions by summing all the sessions that have only one view. Then we can get the percentage of bound sessions by branding them out of total sessions and multiplying by 100. Again, we see a clear formatted alias and quite a complex spell this time. However, we don't have to worry that we'll make a mistake because Python will handle the mathematical operations correctly if we define our metrics correctly. Okay, our cube will also meet dimensions. Here we define a single dimension class in the same manner as the metric class. We are using either the same variables, aliases and fields. Initializing this class, we create a boundary dimension for our cube. and we define a cube class. The cube accepts metrics, dimensions, and attainable as arguments. For dividing reasons, we also store the time the qubit was created. And it has a property SQL, which will return an SQL query of all the things that we wish to know. It will select dimensions and edges from the table if we wish for the SQL to work. Then we also need to group by the dimensions, and this is what 2. Furthermore, we can pass all of the metrics and dimensions that we previously defined to the queue. We can imagine that the user is analyzing data on a data visualization tool, say Looker, and he or she selects these metrics and dimensions. We also pass a table called Minerva. Minerva was a Roman goddess of wisdom. Then we read the SQL code, all the cube, and we get this eat SQL query. In the end, we define 3 classes, a metric class, and the dimension class, and the cube class. Out of the metric class, we created 4 metric objects from scratch, and we derived 3 metric objects from all of them and numbers. That created 1 dimension object, month, and 1 cube object, quadrant, the Minerva cube. This cube object is very easy to spawn, and it gives us a neat SQL query that we can use to query analyze data with. We made all of this using friendly Python classes, and with this, we include the practical part. Lastly, I can add that the full beauty of friendly Python classes losses for the number of objects, as well as their title and rows. To experience it, please try it yourself. This is it. To recap, we answered why do we need classes. We don't need to use classes Python, but they help with organized code and sometimes libraries in force. Then we discussed instruments that we use to make prep classes, data classes, operators, and composition. Then we defined a friendly class as a friend in real life, easy to understand, to talk to, understands without words if there's such need, easy to reach, or easy to call. We stepped through examples of forging a friend matching. And at the end of everything, we practiced the concept. This is the literature that I drew the knowledge from. Highly recommended, fluent by Luciano Ramalho, and a proposition over heritage principle by Brad wrote this. If you were 3 bio breakers, I had a few exercises prepared for you. You can work it out. The tasks are to implement metrics addition and subtraction support, integrate and derivative metric based on at least 2 mathematical operations with other metrics. If you would like to run the code yourself, please visit my email account to find the link to the Google Colab notebook. Make a copy of the notebook to have full control of it. There you can also buy my content details. And that's a wrap. Would you believe for family classes? Do you have questions?